Hello there, and welcome to the Sleepy Space Channel. Tonight we'll be drifting outward, past the last warm edges of starlight, into the long and open spaces between the stars, where certain worlds travel without a sun to call their own. These are the rogue planets, free-floating, unhurried, held only by their own gravity and the slow turning of the Milky Way. Some of them have been wandering since long before our sun existed. Some carry iron weather in their clouds, and some keep oceans liquid in their depths, warmed entirely from within, without a single ray of starlight ever reaching them. Tonight, we'll move among them softly and learn what it means for a world to carry its own warmth through the dark. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, too. One sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your shoulders soften. Let your breathing slow. Allow your eyes to grow heavy, and let the day quietly fall away. Let's begin. There is a particular quality to the darkness between the stars. It is not the darkness of a room at night, where walls exist somewhere just beyond sight, where familiar things wait for morning. It is something older than that, and more spacious, a darkness that has no edge, no ceiling, no floor. It moves through you rather than surrounding you. And within it, moving quietly and without ceremony, there are worlds. You might allow yourself, just for a moment, to imagine leaving everything behind. Not dramatically, not in a rush, simply drifting outward, the way a thought sometimes drifts when you are almost asleep. The sun grows smaller behind you. Its warmth becomes a memory rather than a sensation. The planets of your own familiar system recede, each one a smaller point of light than the last, and then the sun itself becomes simply another star among many. And then it too is gone, folded into the general quiet of the Milky Way's long, slow turning. You are now somewhere between the stars. And it is not empty here. Rogue planets move through this space with a quietness that matches the environment around them. They do not announce themselves. They carry no light of their own, or almost none. They do not orbit anything that would make them easy to find. They are planetary bodies, genuinely planetary in their mass and their structure, and the geology locked inside them. But they travel alone, unbound to any sun, held only by their own gravity and the very slow, very large gravitational pull of the galaxy itself. This is not a strange or unusual fate for a planet to have. That is one of the first gentle surprises of rogue worlds. They are not exceptions, not accidents, not oddities that somehow broke the rules of planetary formation. They are, in many ways, a natural and expected outcome of the way planetary systems come together. Worlds are born in conditions that are crowded and gravitationally complex, and the process of settling into stable orbits is not always clean. Some worlds never find a stable orbit. Some are nudged, slowly or suddenly, onto paths that lead away from their stars and into the open galaxy. Others may never have belonged to a star at all. And so they drift, quietly, continuously, in the slow galactic current. The darkness around a rogue planet is not a punishment or a loss, though it is easy to frame it that way at first. Darkness here is simply the natural state of interstellar space, the baseline condition from which stars are the exception. A rogue planet exists within that baseline. It moves through the galaxy without the organizing presence of a sun, without the rhythms of sunrise and season, without the illumination that we, from our own sun-centered perspective, might instinctively associate with a world being properly alive. But alive is a complicated word, because some of these worlds carry warmth within them. Not the warmth of reflected starlight, not the warmth of solar radiation absorbed and released something older, something that does not depend on a star at all. Internal warmth. The slow, quiet burning of a planet's own formation heat, still bleeding outward after billions of years. The patient energy of radioactive decay, turning mass into heat in the deep interior. And in some cases, a thick atmosphere acting as a blanket, holding that warmth close, keeping it from escaping entirely into the cold of interstellar space. And so the question that will carry us gently through this night is this: if there is no star, what allows a world to remain warm at all? It is a question worth sitting with. Not urgently, not anxiously, just as a soft thread to follow, the way you might follow a sound in a quiet room without needing to know exactly where it leads. The answer will come in its own time, and by the time it arrives, you may already be somewhere between waking and sleep, drifting in your own quiet, following the slow motion of worlds that have been moving through the dark for longer than the Earth has existed. So let us begin. Let us go slowly. There is no hurry here. The rogue planets have been drifting for billions of years, and they will still be there at the end of this night, and at the end of many nights after that. A rogue planet is, at its most essential, a planetary mass object that does not orbit a star. That definition sounds simple enough, and it is, but the simplicity of the definition holds within it a great many things that are worth unfolding slowly, because each one of them quietly changes the picture of what a planet is and what a world can be. When astronomers speak of planetary mass objects, they mean bodies whose mass falls within a certain range, large enough to have formed into a rounded shape under their own gravity, large enough to have internal structure and perhaps an atmosphere, but not so large as to begin the process of nuclear fusion that would make them a star. A planet's mass is the mass of a world, and a rogue planet, for all that it travels alone, still has that mass. It is still a world in every structural sense of the word. What it does not have is a gravitational bond to a star. It moves through the Milky Way's disk freely, following its own trajectory through the galaxy, affected by the large-scale gravitational pull of the galaxy's collective mass, but not by the more immediate, more intimate pull of a nearby sun. In a way, you might say that rogue planets orbit the galaxy directly. Their path is not a small ellipse around a warm central body. It is a vast, slow arc through the structure of the Milky Way itself, a journey that takes hundreds of millions of years to complete a single loop. This means something quite specific about time on a rogue planet. On Earth, time is structured by the sun. The day is the period of one rotation, the time it takes for the planet to turn once relative to the direction of the sun, so that a single point on the surface moves from light to dark and back to light again. The year is the period of one orbit, the time it takes to travel once around the sun, through all the seasons that arise from the angle of the planet's tilt. Both of these fundamental units of time, the day and the year, are defined by the relationship between a planet and its star. A rogue planet has no year in this sense. There is no orbit to complete, no annual cycle of closer and farther, no seasons produced by a changing angle of sunlight, because there is no sunlight to fall at any angle at all. Time, on a rogue planet, is stripped of one of its most familiar layers. What remains is rotation. The planet still turns on its axis, that motion is internal, a product of the angular momentum preserved from the planet's formation, and it does not require a star to continue. So there is still a kind of day on a rogue planet, still a cycle of a single point on the surface returning to the same orientation relative to the distant stars. But that cycle is defined not by light and dark. Both sides of the planet are equally dark, but simply by the rhythm of the turning itself. Imagine, then, standing on the surface of a rocky rogue planet, if it had a surface to stand on. The sky above you would be full of stars, but they would be the same stars at noon as at midnight, because there is no noon, no midnight, no shadow cast by a rising sun. The stars would wheel slowly overhead as the planet turned, the way stars wheel at night on Earth. But they would always be there, never washed out by any brighter light. The Milky Way itself might be visible as a band of faint, cold luminosity arching across the sky, not as a navigational aid or a seasonal marker, but simply as a constant background, the soft structure of the galaxy made visible. There would be no horizon brightening before sunrise, because there is no sunrise. There would be no golden hour, no twilight, no color shifting in the atmosphere as a star climbs the sky. What light there is, and there is some, from the stars themselves, from distant galaxies, from the faint background radiation that fills all of space, would be consistent, cold, and very faint. The sky of a rogue planet is a night sky, but a night sky that never ends. The planet's identity as a planet, however, remains entirely intact. Gravity still shapes it. An iron-nickel core, if the planet is rocky and large enough to have differentiated its interior during formation, still sits at the center, dense and perhaps still partially liquid, driving geological processes from within. A silicate mantle still moves, slowly, in convective cycles. If the planet is large and has retained an atmosphere, that atmosphere still circulates, driven by temperature differences that arise not from solar heating, but from the planet's own internal warmth, pushing upward from below. The planet is structured, layered, internally dynamic, a world in the fullest sense, and none of that requires a sun. It is worth pausing on this, because it runs counter to something very intuitive. We tend to think of planets as objects defined partly by their relationship to a star, as members of a system, as bodies in orbit, as places that receive a certain amount of light and heat from a central source. A planet without a star feels, at first, like something incomplete. But the planet itself does not experience incompleteness. Its mass is what it is. Its structure is what it is. The processes operating inside it are driven by physics that does not consult the star. The planet exists on its own terms. This is, in fact, one of the gentler philosophical reframings that rogue planets offer. They suggest that a world does not require illumination from outside to be fully itself. That a planet's reality, its geology, its gravity, its slow internal processes, is prior to and independent of the light that falls on it. Light is something that happens to a planet from the outside when there happens to be a nearby star. But the planet is something else, something deeper, something that exists regardless of whether the light arrives or not. The Milky Way is the context within which rogue planets move. Our galaxy is a broad, flattened disk of hundreds of billions of stars, with spiral arms wrapping outward from a denser central bulge, the whole structure slowly rotating over timescales that dwarf even stellar lifetimes. Rogue planets move within this disk, distributed roughly along the same plane as the stars, following orbits that are shaped by the overall gravitational potential of the galaxy. They are not gathered into tight clusters, not found only in certain regions. They are spread through the disk as a kind of quiet, invisible population, interleaved with the stars, but not attached to them. The interstellar medium, the thin gas and dust that fills the space between stars, is the immediate environment of a rogue planet. It is extraordinarily sparse by any everyday standard, barely measurable, even over enormous distances, but it is present. A rogue planet moves through this medium continuously, and the medium has its own properties, its own faint temperature, its own occasional density variations where molecular clouds gather and slowly thicken. A rogue planet is not moving through perfect emptiness, even if the emptiness is very nearly complete. And so it continues, turning slowly, moving through the long galaxy, carrying its own warmth and its own structure through a darkness that is not absence, but simply distance. Not void, but simply the natural state of the space between things. Planetary systems are not born in stillness. They begin in motion, in the rotating, collapsing disk of gas and dust that gathers around a newly forming star, where matter is constantly in motion, clumping and fragmenting, grains sticking together, larger bodies sweeping up smaller ones, the whole system slowly sorting itself by gravity into the structures we recognize as planets. This process is not orderly. It is not gentle, at the scale of decades or centuries. It is a long, slow gravitational negotiation among dozens or hundreds of objects, each one pulling on all the others, and the outcome is not always a stable, well-spaced family of worlds circling their star in neat ellipses. Sometimes a planet gets pushed out. The mechanism is gravity. The same force that holds planetary systems together is the one that, under the right conditions, can unravel them. In the early life of a planetary system, when there are many large bodies still in relatively close proximity, gravitational interactions between them can be quite significant. Two large planets, passing relatively close to one another during a particularly unstable phase of the system's development, can exchange energy in such a way that one is pushed inward toward the star and one is pushed outward. If the outward push is large enough, the planet's velocity exceeds what the star's gravity can hold, and the planet is released. Released is perhaps the right word. It suggests something gradual rather than violent, and in many cases the process is indeed gradual. The sequence of gravitational nudges that ultimately sends a planet across the threshold of escape velocity might play out over millions of years, each individual interaction small, the cumulative effect growing slowly until the planet's orbit becomes hyperbolic rather than elliptical, and it begins to move away from its star on a path that never turns back. From the outside, watching over geological timescales, it would look less like an explosion and more like a slow, quiet departure. The threshold itself, the escape velocity, is simply the speed at which a planet's kinetic energy equals the gravitational potential energy binding it to the star. Below that threshold, the planet's path curves back, bound by the star's pull no matter how far it travels. Above it, the planet continues outward indefinitely. The transition from bound to unbound is not experienced as a dramatic event. There is no sound, no visible boundary, no moment when the planet knows it has crossed the line. There is only the gradual, then permanent, recession of a distant star. Not all ejections come from within a single planetary system. Rogue planets can also be produced by the environments in which stars form. Young stars are born in clusters regions where many stars form simultaneously from the same large cloud of gas and dust. In these clusters, stars are initially much closer together than they will be when the cluster disperses over time. A planet forming around one young star in a dense cluster might find its early orbital development disrupted by the gravitational influence of a neighboring star passing at relatively close range. The neighboring star is not trying to steal the planet. It is simply present, and its gravity is present, and the cumulative effect of many such close stellar passages can destabilize young planetary orbits before they have fully settled. Some rogue planets follow yet another path to their solitary state. They never belonged to a star in the first place. The process of star formation, the gravitational collapse of a region of a molecular cloud, does not always produce just one object. Large collapsing regions fragment. A fragment large enough to form a star does so. A fragment somewhat below that threshold produces a brown dwarf, an object that begins the collapse but never achieves the core temperatures necessary for sustained hydrogen fusion. And a fragment smaller still below the mass threshold for brown dwarf classification produces something that looks very much like a planet but formed in isolation, through the same gravitational collapse process that makes stars, rather than through the gradual accumulation of solids in a protoplanetary disk. These objects, sometimes called free-floating planetary mass objects or substellar objects, occupy an interesting boundary in the classification of astronomical bodies. Are they planets if they never formed around a star and were never in the orbit of one? The word planet carries implications of a certain formation history and a certain relationship to a central star. But in terms of mass, in terms of structure, in terms of everything physically measurable about them, they are indistinguishable from rogue planets that were ejected from a stellar system. They drift through the same interstellar space. They evolve under the same physics. They are, to all practical purposes, the same kind of object. This blurriness at the boundary between categories is something that astronomy encounters often. The universe does not organize itself according to the definitions that are convenient for human classification. Objects exist on continuums, and the lines drawn between categories, between planet and sub-brown dwarf, between brown dwarf and star, are useful approximations drawn across what is, in physical reality, a smooth distribution of mass and formation history. Rogue planets sit at one end of that continuum, and their existence reminds us that the neat family portrait of a solar system, with its central star and its well-behaved orbiting planets, is one outcome among many, perhaps not even the most common one. What is most striking, if that word can be used softly, is the sheer normality of ejection as a process. Models of planetary system formation that take into account the gravitational dynamics of young, crowded systems consistently find that some ejections are expected. Not every system ejects planets. Many systems apparently form and settle into relatively stable configurations without losing any members. But across the population of all planetary systems, the production of rogue planets appears to be a routine byproduct. For every stable solar system producing planets that stay obediently in orbit, there may be at least one rogue world drifting through the galaxy from a system that did not hold together quite so cleanly. The galaxy, then, has been producing rogue planets since the very beginning of star formation billions of years ago. Every generation of stars forming and developing planetary systems has contributed to the population of free-floating worlds. Some of those worlds are ancient, formed, and ejected in the first billion years of the galaxy's life, long before the Sun existed. Others are geologically young, ejected from systems that formed more recently. They move through the same interstellar space, the ancient and the recent, all of them following the slow galactic current, none of them aware in any sense of the stars they left behind or the darkness they now inhabit. And they carry, in their interiors, the signatures of their origin. Their composition, the ratio of rock to ice to gas, the elements locked into their mantles and cores, tells a story about where, in a planetary disk, they formed, how close to their original star, what temperatures and pressures they experienced during their youth. A rogue planet rich in water ice likely formed far from its original star, in the cold outer reaches of a protoplanetary disk. A rogue planet with a dense, rocky interior likely formed closer in, where temperatures were too high for ice to survive in solid form. These compositional signatures persist even after billions of years of isolated travel, quiet records of a youth that unfolded in a very different environment from the one the planet now inhabits. The sky holds many things that cannot be seen in ordinary light. Rogue planets, if they can be detected at all, reveal themselves in infrared wavelengths, the part of the electromagnetic spectrum that carries heat rather than visible light. An object that glows with internal warmth, even faintly, even far from any star, produces a signature in infrared that sensitive telescopes can detect. And from those detections, a small but growing catalogue of rogue planetary mass objects has been assembled, individual worlds, real and identified, drifting through their specific corners of the galaxy. The first of these that deserves a gentle visit is known by the designation PSO J31, 8.5-22. The name is unwieldy, assembled from catalogue conventions rather than poetry. But the object itself is genuinely interesting, and interesting in ways that are easy to appreciate. It is a young world, young by planetary standards, which means it has existed for only tens of millions of years rather than billions. At that age, a gas giant-sized planet has not yet had time to radiate away all of the heat generated during its formation. The gravitational collapse that made it, and the subsequent compression of its interior, generated enormous quantities of heat, and much of that heat is still present. PSO J31, 8.5-22, glows because of this. Not visibly, not with anything like the warm gold of a star, but in infrared, it is detectable, a warm body drifting freely through a region of the galaxy that contains other young stars and young objects from the same general episode of formation. It was identified because it shared a pattern of motion with a young stellar group nearby, a loose family of stars that formed from the same cloud of gas and dust and still move together through space, though they are not bound as a cluster. The rogue planet was moving with them, having likely formed from the same cloud, though it lacks the mass to have ignited as a star. What is especially gentle and interesting about PSO J31 8.5-22 is its atmosphere. The temperatures at its outer atmospheric layers, still warm from the formation heat that has not yet fully dissipated, are high enough to produce clouds. But these are not clouds made of water vapor and ice crystals, the way clouds on Earth are. They are clouds made of iron. The temperatures in the upper atmosphere are sufficient to vaporize iron, and as that vapor rises and then encounters somewhat cooler layers above, it condenses, just as water vapor condenses into droplets in Earth's atmosphere, forming fine particles of iron that drift in layers, creating the kind of patchy, variable cloud coverage that is familiar from weather systems but composed of something fundamentally different from anything in the sky above your head tonight. Astronomers have been able to infer the presence of these iron-rich clouds because the brightness of PSO J31 8.5-22 changes subtly over time. As the planet rotates, different portions of its cloud-covered atmosphere come into view, and some portions are more heavily clouded than others. The variation in brightness, small but measurable, suggests weather. An active, churning atmosphere in which clouds form and dissipate, in which temperature differences drive circulation, in which something recognizable as meteorology is happening, just with materials that would be alien to any experience of weather you have ever had. This is a world still cooling, still dynamic, still expressing the energy of its own formation in atmospheric processes. It will not always be this way. Over hundreds of millions of years, PSO J318.5-22 will cool. Its iron clouds will thin and eventually disappear as temperatures drop below the threshold for iron vapor. It will become quieter, colder, dimmer in infrared. Eventually, it will be undetectable by any current technology, another dark body among the dark bodies that fill the galaxy's spaces. But for now, it glows gently, and we can find it. Moving to a very different kind of rogue world, one far older and far colder, the object designated WISE 085 5-0714. The designation comes from the WISE telescope, an infrared space observatory, and the numbers encode its position in the sky. This is one of the closest known rogue planetary mass objects to our own solar system, close enough that its proximity to us makes it, paradoxically, one of the most accessible examples for study, even though it is extraordinarily dim. WISE 085 5-0714 is cold. Not merely chilly, not simply cool, this is an object whose outer atmosphere has temperatures that approach, and in some measurements may even fall below, the freezing point of water. It is one of the coldest free-floating objects ever detected. Its surface, if surface is the right word for the upper boundary of a dense, cloudy gas giant atmosphere, is somewhere in the range of temperatures where water not only exists as ice, but where complex atmospheric chemistry becomes possible, where clouds of frozen water and possibly frozen ammonia might drift in thick layers. Detecting an object this cold at all is a challenge. The colder an object is, the less infrared radiation it emits, and the more difficult it becomes to distinguish from the background. WISE 085 5-0714 was found only because infrared astronomy has become sensitive enough, and because it is close enough to us a few light years. In astronomical terms, a neighborly distance, that even its faint emission could be captured. It moves measurably across the sky over the span of years, a tiny shift in position from one observation to the next, the parallax and proper motion that confirm it is a nearby object rather than a distant one. What is quietly beautiful about WISE 085 5-0714 is that it represents what most rogue planets are probably like in the older parts of the galaxy's population. Young rogues are warm and detectable. Old rogues have had time to cool towards something approaching equilibrium with the very faint radiation that fills interstellar space. They are cold, they are dark, they are nearly invisible, and yet they exist in great numbers. WISE 0855 -0714 is the exception in being close enough to find. Most of its kind are invisible to us, drifting through the galaxy in a silence that is purely physical rather than metaphorical. A third world worth visiting is SIMP-J 0136 566 3+09334373, which carries one of the longer and more cryptographic designations in the catalogue of known rogue objects. What makes this world notable, and what makes it worth including in any gentle tour of rogue planets, is its magnetic field. Strong magnetic fields around planetary mass objects are unusual and interesting. A magnetic field of the strength measured around SIMP-J 0136 5663 plus 0933 is comparable in some ways to the magnetic fields around gas giant planets in our own solar system. Fields that produce auroras, glowing displays of light generated by charged particles interacting with the magnetic field lines and being funneled toward the poles. Auroras on a rogue planet would be visible in radio wavelengths, and they have been detected around SIMP-J 0136 5663 plus 0933 The energy driving those auroras does not come from a nearby star. There is no nearby star. It comes from the interaction of the planet's magnetic field with the plasma that the planet itself generates, and from the slow interaction with the sparse interstellar medium. The planet is not passive, not simply a cold rock moving through dark space. It is actively generating electromagnetic phenomena, crackling quietly with a kind of auroral light that no eye is there to see, in a part of the electromagnetic spectrum that is invisible anyway, but real nonetheless. This suggests that rogue planets can sustain a form of internal energetic activity that is not dependent on their relationship to a star. The interior of a planet, massive enough and rotating rapidly enough, can generate a magnetic dynamo, the same process that generates Earth's magnetic field, and that dynamo produces a field that extends outward from the field, planet, into the surrounding space. Charged particles interacting with that field produce radio emissions. The process is quiet, continuous, and entirely self-contained, driven by the physics of the planet's own interior. A fourth world in this tour is OTS-44, an object that offers something different again, evidence that rogue planets can themselves be the gravitational center of nascent systems. OTS-44 is surrounded by a disk of material gas and dust, and perhaps larger particles orbiting around it. This is a circumplanetary disk, the kind of structure from which moons form around gas giants in a conventional solar system. The disk around OTS-44 suggests that moon formation is possible around a free-floating planetary mass object, that the same process of accretion and aggregation that produces moons in a stellar system can occur in isolation, organized not by a star, but by the planet-scale gravity of the central body. This is a gentle but profound observation. It means that planetary systems, the hierarchical arrangement of a larger body with smaller orbiting companions, can form at multiple scales and in multiple contexts, not only around stars. A rogue planet with moons is a system unto itself, however small. It is a gravitational center with gravitational satellites, orbiting the galaxy as a unit, carrying its own miniature architecture through the dark. Each of these objects, PSO J318.5-22, Y0855-0714, SIMP J0136-5663, plus 0933473. OTS-44 is a real place, a real world with real properties moving through real space. They are known not because anyone has visited them or approached them or illuminated them with any artificial light, but because they produced signals, warmth, magnetic activity, gravitational distortion that sensitive instruments could detect across the intervening distances. They are the visible edge of a much larger population that remains, for now, beyond our ability to see. For every rogue planet that has been detected, there are many more that have not. This is not a vague intuition. It follows directly from the physics of detection. Current telescopes can find rogue planets only under certain conditions, if they are young and still warm enough to emit significant infrared radiation, or if they happen to pass in front of a background star and briefly amplify that star's light through gravitational lensing, or if they are close enough to our solar system that their motion across the sky becomes measurable over years of observation. None of these conditions applies to the majority of rogue planets that exist. Most are old, cold, and not conveniently positioned to produce detectable lensing events. The population we can see is a small and biased sample of the total. Estimates of the total population of rogue planets in the Milky Way are genuinely large in some models. They are comparable in number to the stars themselves, or even larger. These estimates come primarily from analysis of gravitational microlensing surveys, which systematically monitor millions of background stars and watch for the brief, characteristic brightening that occurs when a foreground object passes in front of one of them. When the foreground object has no associated star, when the lensing event is caused by something that cannot be seen directly, it can be inferred that the lensing object is a free-floating body, possibly a rogue planet. The duration and shape of the brightening event provides information about the mass of the lensing object, allowing at least rough estimates of whether it is planet-sized, brown dwarf-sized, or stellar. These surveys have found a surprising abundance of short-duration lensing events whose characteristics are consistent with planet mass free-floating objects and whose frequency, when extrapolated across the whole galaxy, suggests that there may be many billions of rogue planets in the Milky Way. Some analyses have suggested numbers that imply several rogue planets for every star in the galaxy. Others produce more conservative estimates. But even the most conservative estimates place the rogue planet population in the hundreds of millions to billions, a background presence that is genuinely significant in the overall accounting of planetary bodies. Within this large population, size and composition vary. The rogue planets most likely to be detected are gas giants, large, initially warm objects that retain their heat longer and produce stronger lensing events. But the underlying physics of planetary formation and ejection suggests that smaller, rockier planets should be even more numerous than gas giants. In stellar systems, rocky terrestrial planets are generally more common than gas giants, and there is no obvious reason why ejection rates would favor one over the other. If rocky rogue planets are at least as common as gas giant ones, possibly more so, then the total number of free-floating rocky worlds in the galaxy becomes very large indeed. The distribution of rogue planets through the galaxy is expected to broadly follow the distribution of the stars that produce them. Most stars in the Milky Way are in the disk, concentrated in the spiral arms and in the regions between them, and most rogue planets should therefore be in the disk as well. The galactic center, where stellar density is higher, may also have a higher concentration of rogue planets, though the dynamics of that region are more complex, and ejection histories there are harder to reconstruct. The outer halo of the galaxy, where stars are sparse and old, likely has a much lower rogue planet density. What this all amounts to is a picture of interstellar space as less empty than it appears. When you imagine the space between stars, the vast distances that separate one stellar system from another, it is natural to think of that space as nearly nothing, as pure vacuum traversed by the occasional photon. And in one sense, it is nearly nothing, in terms of ordinary matter per unit volume. But it is threaded with gravitational influences, laced with the trajectories of cold, dark planetary bodies that produce no light and make no sound and are known about only because of their mass. The galaxy's disk is a kind of quiet crowd in which the rogue planets form the unseen majority. The concept of dark matter provides a useful, if inexact, comparison here. Dark matter is the name given to whatever mass is producing the gravitational effects observed in galaxies that cannot be accounted for by the visible stars, gas, and dust. Rogue planets are not dark matter, they are ordinary baryonic matter, the same stuff as stars and planets and everything we are made of, but they do contribute to the gravitational structure of the galaxy in ways that are invisible to direct observation. They are, in a small and ordinary way, a component of the dark mass of the galaxy, the part that does not shine. To move through interstellar space, then, is to move through a field of invisible worlds. They are there, many billions of them, each one quietly pursuing its galactic orbit, each one carrying its own interior structure and whatever slow processes continue within it. They pass through the same regions where stars exist, through the same molecular clouds where new stars are forming, through the sparse spaces between the spiral arms. They do not interact with each other with any significant frequency. The distances are too large for collisions to be common, or even for gravitational interactions between individual rogues to matter much. They are simply present, each in its own solitude, together forming a population that fills the galaxy. To stand on a rogue planet, if such a thing were possible, and for a rocky rogue it might in principle be imaginable, would be to experience the sky in a way that has no close parallel in any human experience. There would be no sun. This is the first and most fundamental difference, and everything else flows from it. On Earth, the sun dominates every moment of the sky. Even at night, the sun's structures experience sunset and sunrise bound the dark. Moonlight is reflected sunlight. The absence of the sun is defined by its return. On a rogue planet, the sun, whatever star the planet once orbited, or perhaps no star at all, is simply gone. Not absent tonight, not hidden behind clouds, not set below the horizon. Gone entirely and permanently. And the sky is the sky of deep space at all hours of all days for as long as the planet exists. You might imagine the sky. Stars are everywhere. Not the few hundred stars visible to the naked eye from a dark place on Earth, washed out by the glow of the Milky Way and the scattered light of civilization, but the full star field of open interstellar space, thousands of stars visible to any eye sensitive enough to see them, each one a point of cold light that does not twinkle in the way stars twinkle on Earth, because twinkling is caused by Earth's atmosphere bending and scattering starlight, and a rogue planet's atmosphere, if it has one, would produce its own version of this effect, though the details would depend on the atmospheric composition and density. The Milky Way would arch across this sky as a band of faint collective luminosity, hundreds of billions of stars, too distant to resolve individually, their combined light creating a soft structure in the darkness. On Earth, the Milky Way is visible from dark locations on clear nights, a pale arch of light that bisects the sky. On a rogue planet in the galactic disk, this structure would look broadly similar, though its orientation and apparent brightness would depend on exactly where in the disk the planet happened to be. Near the galactic center, the band might appear broader and brighter. In the outer disk, farther from the concentration of stars, it might be a thinner structure. But it would always be there, always present, always the dominant feature of the sky. Stars on this sky would not rise or set in the way that requires a sun for context. They would wheel overhead as the planet turned on its axis, the rotational motion of the planet carrying a point on the surface through a full circle relative to the stars over the course of a day, just as it does on Earth. Certain stars would be visible from a fixed point on the surface only during part of the day. Others, near the celestial poles of the planet's rotation, would remain visible throughout. Over human timescales, decades, centuries, the stars themselves would appear fixed because stellar proper motion is slow enough that it becomes noticeable only over tens of thousands of years. But over the many millions of years of the rogue planet's journey, the stars would shift, the nearby ones moving more quickly against the background of the distant ones, and the sky of the distant future would be subtly different from the sky of today. The surface of a rocky rogue planet, if we allow ourselves to continue imagining such a place, would be shaped by cold and by internal heat in a particular combination. Without a star to warm the surface, temperatures would be extremely low, close to the temperature of the cosmic microwave background, which is just a few degrees above absolute zero, unless the planet's own internal heat managed to produce a meaningful surface temperature. For most rocky rogues, the surface would be bitterly cold, ice and rock, and perhaps thin, atmospheres of nitrogen or other gases that had not entirely been lost to space over the billions of years of travel. The landscape, the word, is being used loosely, and in spirit rather than in literal reference to anything specific, would be shaped by impact craters from occasional meteorite strikes, by volcanic processes, if the internal heat was sufficient to produce volcanism, by the slow creep of ice, if there was any, by the same geological processes that shape worlds throughout the galaxy, just in the absence of weather driven by solar heating. For a gas giant rogue, the experience of standing is not available. There is no surface in the sense of a place where something solid can stand. The atmosphere of a gas giant extends from cold outer layers of hydrogen and helium clouds downward, through increasing pressure and increasing temperature until the gas transitions to a liquid and then to something that behaves more like a metallic fluid. There is no ground, no rock underfoot, just the gradual deepening of pressure and density. Something moving through this atmosphere, if such a thing were possible, would experience only layers, each denser and warmer than the last, eventually reaching pressures that would crush any material structure we are familiar with. But the sky above such an atmosphere, the view from the upper cloud layers of a gas giant rogue, would share the qualities described for a rocky planet's surface. Stars overhead, the Milky Way overhead, no brightening anywhere in the sky that would indicate a sun, just the consistent and permanent starfield of interstellar space. The clouds themselves might glow faintly in infrared if the planet was warm enough, casting a very faint reddish illumination on the layer immediately above them, a self-lit sky, though the light would be too faint and too long in wavelength to be useful to human vision. Time would feel different on a rogue planet, in some abstractly imaginable way. Without the structuring of time by the sun, without the promise of sunrise after night, without the progression of days toward seasons and seasons toward years, time would be measured only by the turning of the planet itself, and beyond that, by the almost imperceptible slow drift of stars as the planet moved through the galaxy. Days would pass, each identical to the last in terms of light, each differing only in which portion of the sky's starfield happened to be overhead at a given moment. Months and years, as human beings understand them, would have no meaning. There would be the day one rotation, and there would be geological time, the timescale of the planet's interior processes, and nothing particularly meaningful in between. This quality of time long, unmarked, defined only by internal rotation and internal geology, gives rogue planets a kind of temporal character that is quite different from anything in human experience. We live on a planet that is, in astronomical terms, extremely busy with solar influences. Tides from the moon, seasons from the axial tilt, the daily rhythm of warming and cooling from the sun's movement across the sky. These things organize our bodies, our sleep, our agriculture, our sense of time's passage. A rogue planet has none of these external influences. Its time is purely its own, driven from within, shaped only by its own rotation and its own internal heat, moving forward at a pace measured in geology and galactic orbital mechanics. The question that was introduced at the beginning of this journey, if there is no star, what allows a world to remain warm at all, finds its answer not in any exotic process, but in something that Earth itself demonstrates quietly, every time a volcano erupts or a hot spring reaches the surface. The interior of a planet is warm. It has been warm since the planet formed, and it remains warm, and the warmth comes from sources that do not depend on a nearby star. The first and most fundamental of these sources is the heat of formation itself. When a planet forms, it does so through the accumulation of smaller bodies, dust grains growing into pebbles, pebbles growing into rocks, rocks growing into planetesimals, planetesimals colliding and merging into protoplanets. Each collision, at every scale, converts kinetic energy into heat. A large impact, two bodies of significant size colliding, releases enormous quantities of energy, most of it as heat deposited in the growing body. A planet that has grown through billions of such impacts over millions of years has accumulated a great deal of heat, and much of that heat is trapped in the interior, unable to escape to space as quickly as it is generated. This residual formation heat persists for billions of years after the collisions have stopped. The early Earth was largely molten because of it, and Earth's interior remains significantly warm today, 4.5 billion years after formation, because the heat from those early impacts is still diffusing outward, A rogue planet carries this formation heat as thoroughly as any planet in a stellar system. The process that made it was the same process, driven by the same physics, producing the same thermal signature in the interior. Whether the planet subsequently stayed in a stellar system or was ejected into interstellar space, its formation heat is its own, and it continues to bleed outward on the same timescale it always would have. The ejection event, however it occurred, does not accelerate or decelerate the loss of formation heat. The planet carries its thermal history into the dark. The second source of internal heat is radioactive decay. Certain elements incorporated into a planet's interior during formation, uranium, thorium, potassium, and others, are unstable. Over time, their atomic nuclei break down, releasing energy in the process. This is not a rapid or dramatic process. It is slow, steady, and continuous, converting the mass of unstable atoms into heat at a rate that is determined entirely by the physics of the nucleus, unaffected by the planet's environment, unaffected by the presence or absence of a star. On Earth, radioactive decay currently contributes roughly half of the total heat flowing outward from the interior. The rest is still escaping formation heat. In a rogue planet, the same two processes operate, in proportions determined by the planet's specific composition and age. The rate of radioactive decay decreases over time, because decay converts unstable atoms into stable daughter products, and once an atom has decayed, it is no longer available to decay again. Shorter-lived radioactive isotopes contribute a great deal of heat in a planet's early life and then fade relatively quickly. Longer-lived isotopes, such as uranium-238 and thorium-232, contribute heat for billions and even tens of billions of years. A rogue planet, several billion years old, still receives a meaningful thermal contribution from these long-lived isotopes, even though its shorter-lived radioactive inventory was spent long ago. These two sources, formation heat and radioactive decay, are the internal heat sources. But the ability of a planet to stay warm also depends on what it does with that heat, and this is where the atmosphere becomes important. A bare, rocky surface in interstellar space with no atmosphere radiates its heat directly to space and cools relatively quickly on geological timescales. But a planet with a thick atmosphere is insulated. The atmosphere absorbs the heat flowing upward from the surface and radiates some of it back downward, creating a greenhouse effect that raises the surface temperature above what it would be without the atmospheric blanket. In the context of a rogue planet, the greenhouse effect operates without any input from a star. There is no solar radiation to drive atmospheric warming from the outside. Instead, the heat source is entirely internal geothermal heat rising from the interior, and the atmosphere acts as a blanket that keeps that heat close to the surface. A rogue planet with a thick, hydrogen-rich atmosphere, perhaps 10 to several hundred times the thickness of Earth's atmosphere by mass, could maintain surface temperatures significantly above what bare radiation into interstellar space would allow. In the most favorable cases, a rogue planet of appropriate mass with a thick, thermally insulating atmosphere surface temperatures might remain above the freezing point of water, or at least above the temperature at which certain chemical processes continue to operate. The possibility of liquid water on a rogue planet is one of the most quietly intriguing aspects of this topic. Water, as the chemistry of life on Earth requires, needs to be liquid. It needs a temperature range that falls between freezing and boiling, a range that on Earth is maintained primarily by the sun's energy. On a rogue planet, the maintenance of that temperature range would depend entirely on internal heat, and it would require conditions that are not impossible but are probably specific. A planet of the right mass, with the right atmospheric thickness, in the right phase of its thermal evolution, might indeed maintain a surface or near-surface environment in which water existed in liquid form. More plausible, and more likely to persist for long timescales, is the possibility of liquid water not at the surface, but beneath it, buried under layers of ice that insulate it from the cold of interstellar space, warmed from below by the planet's geothermal heat. This is exactly the situation that exists on several of the icy moons in our own solar system. Enceladus, a moon of Saturn, maintains a subsurface ocean of liquid water beneath a shell of ice several kilometers thick, warmed not by the sun, which provides very little heat at Saturn's distance, but by tidal heating from Saturn's gravitational influence. Europa, a moon of Jupiter, almost certainly has a subsurface ocean maintained in liquid form by tidal heating as well. For a rogue planet, tidal heating from a star is not available, but the other heat sources are. If the ice shell is thick enough to provide good insulation, and if the internal heat flux is sufficient to warm the water above freezing at the base of the ice, a subsurface ocean can persist for a very long time, potentially for billions of years, depending on the rate of internal heat loss. The ocean beneath the ice would be in darkness the same quality of darkness as the world above the ice, just underground rather than extraterrestrial. It would be an ocean that has never seen light, warmed entirely from below, circulating on its own thermal currents, a body of water entirely self-contained. Convection is the mechanism by which heat moves through the interior of a planet. Hot material rises, carries its heat upward, cools, sinks again, and is reheated from below. This cycle of rising and falling is the engine of geological activity in a planet's interior. It drives the slow movement of tectonic plates on Earth. It powers volcanism. It transports heat from the deep interior to the outer layers. On a rogue planet, convection continues as long as there is sufficient temperature difference between the deep interior and the outer layers to drive the circulation. Early in a planet's life, this temperature difference is large and convection is vigorous. As the planet ages and cools, the temperature difference decreases, convection slows, and eventually, on extremely long timescales, the interior approaches something closer to thermal uniformity. But this is a process measured in billions to tens of billions of years. All of this, the formation heat, the radioactive decay, the atmospheric insulation, the convective transport, forms a self-contained thermal system. A rogue planet, once it has formed and been launched into interstellar space, carries its own energy supply within it, requiring no external input to sustain it for billions of years. The star that once illuminated it, or the star it never had, is irrelevant to this system. The planet persists, warm within, gradually cooling, maintaining its own processes, independent of the larger cosmic environment. The atmosphere of a rogue planet, if it has one, is not a passive envelope. It moves. It circulates. It produces, in a muted and slow version of the atmospheric phenomena familiar from worlds with suns, something recognizable as weather. Atmospheric circulation on a rogue planet is driven by internal heat rather than solar heating. On Earth, the dominant driver of atmospheric circulation is the uneven solar heating of the surface. The equator receives more energy from the sun per unit area than the poles, creating temperature differences that drive large-scale circulation patterns. On a rogue planet, solar heating is absent, but internal heat flux from the planet's interior can create temperature differences at the surface that drive a circulation of their own. If the internal heat emerges unevenly more strongly in some regions than others, due to variations in crustal thickness or geological activity, then those temperature differences can set the atmosphere in motion. On a gas giant rogue, the situation is somewhat different, but the principle is the same. The deep interior is warmer than the outer layers, and this temperature gradient drives convection through the entire atmosphere. Warm gas rises from depth, cools as it approaches the outer layers and sinks again. This convective turnover produces cloud layers, generates wind patterns, and creates the banded structure seen in the atmospheres of the solar system's gas giants. Though on a rogue gas giant, the patterns might be organized differently, without the day-night temperature differences that also contribute to weather on planets with stars. Clouds on a rogue planet would be made of whatever condenses at the temperatures present in its atmosphere. For a young, warm, rogue gas giant, the temperatures in the upper atmosphere might be high enough for iron and silicate clouds, as discussed in the case of PSO J318.5-22. For an older, cooler rogue, the cloud chemistry shifts to different compounds, metal sulfides at intermediate temperatures, then water ice clouds at still cooler temperatures, then ammonia ice clouds at temperatures below that. Each temperature regime produces a different kind of atmospheric chemistry, a different kind of cloud, a different kind of weather. The clouds persist and evolve on timescales that might be very long by human standards. Storm systems on a rogue planet with no seasonal forcing and no day-night cycle to organize them might persist for thousands or millions of years before dissipating. Lightning is possible in dense, turbulent atmospheres where charge separation can occur. On Earth, lightning is produced in storm clouds, where updrafts and downdrafts separate electrically charged particles, building up a potential difference that eventually discharges as a bolt. In a dense, convective rogue planet atmosphere, similar processes might produce lightning, though without a stellar-driven weather cycle, the character of these discharges might be different, perhaps more sustained, perhaps less frequent. The slow crackle of a continuously convecting deep atmosphere, rather than the punctuated drama of thunderstorms. The lightning, if it exists, would add a faint electromagnetic glow to the cloud layers, invisible from outside but present within, a quiet electrical discharge in the dark. Magnetic fields add another layer of subtle activity. The magnetic dynamo process, in which the rotation of a conducting fluid, such as liquid iron in a rocky planet's core or metallic hydrogen in a gas giant's interior, generates a magnetic field, operates without reference to any external source of energy. It is driven by the rotation of the planet and the thermal convection of the conducting fluid, both of which continue on a rogue planet exactly as they do on planets in stellar systems. The magnetic field that results extends outward from the planet into the surrounding space, forming a magnetosphere, a region of space dominated by the planet's own magnetic field rather than by any external field. Interstellar space is not empty of charged particles. The solar wind, the stream of charged particles emitted by the Sun, fills our solar system and eventually merges into the broader interstellar medium at the heliopause. Beyond the heliopause, the interstellar medium itself contains a sparse population of charged particles, cosmic rays from distant sources, the remnants of stellar winds from other stars, the background plasma that threads through the galaxy. A rogue planet with a magnetic field interacts with these particles. Its magnetosphere deflects some of them, funnels others toward the magnetic poles, and produces a faint but real electromagnetic interaction with the interstellar environment. At the magnetic poles, charged particles funneling into the upper atmosphere produce auroras. Not the brilliant curtains of green and red that shimmer over Earth's polar regions, powered by the dense solar wind, but fainter, more continuous emissions, generated by the slower but persistent interaction of the interstellar medium with the planet's magnetic field. These auroras would be in radio wavelengths, the same radio emission detected from SIMP J01365663 plus 09333473, rather than invisible light. But they would be real physical phenomena, produced by real particle interactions, evidence of a planet that is not simply an inert body, but an active electromagnetic participant in the galaxy's environment. The light emitted by a rogue planet, in all these processes, is faint. It is the glow of warm atmospheric layers in infrared. It is the radio emission of auroral processes. It is, for very young rogues, a faint, visible glow from the hottest atmospheric layers. It is nothing like the brilliant point of a star, nothing like the reflected glow of a sunlit planet. But it is not nothing. A rogue planet is not perfectly dark. It has its own luminosity, modest and spread across wavelengths that human eyes cannot see, but present a quiet self-expression that persists as long as there is warmth to express and a magnetic field to organize. These subtle emissions carry information. They tell astronomers about the temperature of the atmosphere, the composition of the clouds, the strength of the magnetic field, the rate of rotation. They are the means by which we know about rogue planets at all. The faint, persistent emission of a world carrying its own warmth through the dark. This is the signal that reaches telescopes across light years of distance, the only evidence that something is there, the tiny whisper of physics operating in the cold between the stars. There is a tendency, when thinking about isolated objects in space, to imagine them as perfectly still, as if removed from the organizing presence of a stellar system, with its planets in motion and its seasons and its rhythms, a rogue planet would simply drift to a halt. This intuition is understandable. We associate motion with purpose, with orbit, with the centripetal logic of a system organized around a center. Remove the center, and the imagination reaches for stillness. But stillness is not available in the galaxy. Everything in the Milky Way is in motion, and rogue planets are no exception. There is no position in the galaxy, no region of interstellar space, no distance from any star at which an object can simply stop. Motion is not a property that stellar systems impose on their members. It is a property of existence within a gravitational structure as large and complex as a galaxy. The motion of a rogue planet through the galaxy is not the tight, rapid ellipse of a planet around its star. It is an orbit of an entirely different character and scale and arc through the gravitational potential of the entire galaxy, shaped by the combined pull of all the stars, all the gas, all the dark matter distributed through the Milky Way's disk and halo. This galactic orbit takes hundreds of millions of years to complete. During a single human lifetime, even during the entire span of recorded human history, a rogue planet's galactic orbit is utterly imperceptible in its progress. It completes a negligible fraction of a degree of arc. The rogue planet is moving continuously and at great speed by any everyday standard, and yet the arc it traces against the background structure of the galaxy is so vast that the motion registers only across timescales that human intuition cannot directly grasp. We can calculate it, describe it, place it in context, but we cannot feel its scale in the way we feel the motion of a thrown object or a passing vehicle. At this scale, motion becomes something to understand conceptually rather than to experience. A rogue planet moves at a speed of hundreds of kilometers per second relative to the galactic center. A genuinely large velocity in everyday terms, fast enough to cross the distance from Earth to Moon in a matter of seconds. But the distances are so enormous that this motion, sustained for millions of years, covers only a modest arc across the structure of the galaxy. The solar system itself moves at a comparable speed around the galactic center, completing one full orbit roughly every 230 million years. This is sometimes called a galactic year or a cosmic year, and in these units, the solar system is about 20 galactic years old. Rogue planets in the galactic disk have similar orbital velocities and similar periods, adjusted for their specific positions and the gravitational influences they have experienced. They are participants in the same slow wheel, governed by the same deep gravitational architecture, moving at the same general pace as everything else embedded in the disk. The paths of rogue planets and the paths of star systems are interleaved within the galactic disk. They pass through the same regions, follow the same general galactic structure, experience the same large-scale gravitational influences. The disk of the Milky Way does not sort its contents neatly into stars with planets on one side and free-floating objects on the other. Everything moves together, mixed and interwoven, on orbits that cross and recross over millions and billions of years. Occasionally, the path of a rogue planet brings it relatively close in galactic terms to a star system. In purely mathematical terms, the probability that a rogue planet will pass close enough to a stellar system to have its trajectory significantly altered by that system's gravity is very low over a single galactic orbit. The distances between individual stars are large enough, and the orbits of rogue planets are random enough in their directions and inclinations that genuinely close encounters are simply rare. But rare, across billions of years, and hundreds of galactic orbits, and a galaxy containing hundreds of billions of stars and potentially trillions of rogue planets, still means that such encounters have happened, are happening now, somewhere in the galaxy. Too distant and too slow to observe on any human timescale. Our own sun has likely passed within a light year or two of various stellar neighbors over its 4.5 billion years of existence, simply because the disk of the Milky Way has been churning through those timescales with billions of stars all in motion. Some of those neighbors presumably had rogue planets in their vicinity. Some rogue planets have presumably passed through the outer reaches of the solar system at some point in its history, so distant and so faint that they were never detected and their passages were completely unnoticed. The solar system has not been isolated in the way that a planet in a room is isolated. It has been part of a slow galactic current that has brought it into the same neighborhood as many different stellar systems and their associated populations of dark, cold, free-floating objects. The Oort cloud, the outermost and most tenuous component of the solar system, extends perhaps a quarter of the way to the nearest star. Objects passing at such distances would experience a weak but real gravitational nudge from the Sun, their trajectories bent slightly, their velocities changed by a small fraction. Whether any such object was ever perturbed inward toward the inner solar system and arrived as what appeared to be an unusually strange comet is not a question that can currently be answered definitively. But it is a question that astronomers take seriously. This galactic-scale thinking has a particular quality of calm associated with it. The individual dramas of planetary formation and ejection, the close encounters between young planets, the gravitational perturbations, the chaotic instabilities that flung worlds out of their birth systems into the interstellar dark, all play out against a backdrop of almost incomprehensible size and duration. The galaxy does not notice them. The slow turning of the Milky Way continues at its own pace, indifferent to whether any particular planetary body is in orbit around a star or drifting freely between them. What registers as catastrophe at the scale of a planetary system, the ejection of a world from the only gravitational community it has ever known, is, at the galactic scale, an entirely ordinary rearrangement of mass, no more significant than the shifting of a few grains of sand on a beach, whose extent cannot be seen from any single position. Rogue planets participate in the galaxy's turning as fully as any star, any stellar system, any nebula. They are structural elements of the galaxy, players in the galactic gravitational game, not oddities or outliers, but participants in the same slow cosmic choreography as everything else. The interstellar medium through which rogue planets move is not a perfect vacuum. It is sparse, far sparser than the best vacuum achievable in any laboratory on Earth, but it is not nothing. It consists of gas, primarily hydrogen in various forms, and dust and magnetic fields, and the diffuse radiation backgrounds that fill all of space. Rogue planets moving through this medium experience a very faint resistance, not enough to meaningfully slow a planet over any practical timescale, but enough to gradually erode the very outermost layers of an atmosphere, atom by atom, over billions of years. The mechanism is a combination of direct sputtering, in which particles of the interstellar medium collide with and dislodge atmospheric molecules, and the slow photoionization of the upper atmosphere by the diffuse ultraviolet background that permeates the galaxy even far from any individual star. This erosion is extremely slow, and for large rogue planets with massive atmospheres, the gas giants and super-Jupiters that make up the more massive end of the rogue planet population, it is entirely negligible. A gas giant rogue planet could drift through the interstellar medium for the current age of the universe and lose an utterly trivial fraction of its atmospheric mass to this process. But for smaller, rocky rogue planets with thin atmospheres, the cumulative effect over cosmic timescales might be significant, a slow thinning of the atmospheric envelope as the planet drifts through the sparse but persistent interstellar gas. This process too is quiet, continuous, and unhurried, matching the overall character of rogue planet existence. The galaxy's disk is also not uniform in its structure. Spiral arms are regions of somewhat higher stellar density, where gas and dust are compressed by density waves moving through the disk, triggering episodes of star formation. These are not solid structures that rotate with fixed positions, they are wave patterns, pressure enhancements that move through the disk at their own speed, which differs from the orbital speed of individual stars and planets. A star, or rogue planet, does not stay in a spiral arm permanently. It passes through spiral arms periodically as its orbit and the arm's pattern speed drift relative to each other. Between the spiral arms are inter-arm regions of somewhat lower density, where star formation is slower and the overall density of objects is lower. A rogue planet, over hundreds of millions of years of galactic orbit, passes through both, through the relatively busier environment of a spiral arm, where new stars are forming and young, hot objects glow relatively brightly, and where the density of gas and dust provides slightly more material for interaction with the planet's outermost layers, and through the quieter inter-arm regions, where the background is darker and the density of neighbors somewhat lower. Through all of these environments, the rogue planet continues its trajectory, unaffected in any dramatic way by the changing density of its surroundings, slowly turning, slowly cooling, slowly moving. There is something to consider in the accumulated distance. Over a single galactic orbit of 230 million years, a rogue planet moving at a few hundred kilometers per second traces a path whose total length is measured in tens of thousands of light-years. Over the lifetime of the galaxy, over 10 billion years or more, a rogue planet has traveled a distance that, if laid out in a straight line, would extend far beyond the local group of galaxies, far into the intergalactic void. It has not traveled in a straight line, of course. It has moved in long, slow arcs, constrained by the galaxy's gravity, returning again and again to the same general regions of the disk, tracing and retracing a path that curves and bends through the same gravitational landscape over and over. But the total distance traveled is real, and it is vast, and it was covered not through any engine or purpose, but simply through the persistence of motion in a universe that offers no friction sufficient to bring a planet to rest. The rogue planet moves because it has always been moving. It was launched into interstellar space with a velocity, and that velocity modified by every gravitational encounter since, bent by the curvature of the galaxy's potential well, nudged and adjusted over billions of years of passage through the disk persists. It will persist for as long as the planet persists, which is to say for a very long time. Through spiral arms and inter-arm voids, through the slowly dimming future of the galaxy, through the long cooling of its own interior, the rogue planet continues its arc. Unhurried, unwatched, uninterrupted, simply moving as everything in the galaxy moves, in the dark and the quiet and the cold, for as long as motion and mass and gravity endure. The lives of rogue planets are long. This is not simply a statement about longevity in the sense of surviving for a long time. It is a statement about the character of these objects, which are structured to persist in a way that stars, for all their brilliance, are not. Stars are engines. Rogue planets are not. The distinction matters enormously when considering what endures in the universe over the longest timescales we can meaningfully discuss. Stars consume themselves. Their luminosity is the product of nuclear burning in the core, the fusion of hydrogen into helium, and then the fusion of heavier elements in the later stages of stellar evolution. This consumption is irreversible. A star burns through its fuel, and when the fuel is exhausted, the star changes in ways that are ultimately catastrophic for its structure. Massive stars end in supernovae, violent, total disruptions that scatter the star's mass across light years of surrounding space in a matter of seconds. Smaller stars like the Sun swell into red giants before shedding their outer layers and collapsing into white dwarfs. The most massive compact remnants become neutron stars or black holes. In none of these outcomes does the original star simply continue to exist indefinitely. The star's brilliance is, in the most literal sense, the process of its own consumption, light purchased at the cost of structural dissolution, bought on a credit that will eventually run out. A rogue planet has no fuel to consume. It does not undergo nuclear burning. Its internal heat sources, residual formation heat and radioactive decay, are finite but enormously long-lived, and even when they are largely exhausted, the planet's structure remains. It does not explode. It does not collapse. It does not shed its mass into space in a final convulsive release. It simply continues to exist, colder and quieter than it was, but physically intact, moving through whatever environment surrounds it, until that environment itself changes beyond recognition. The rogue planet's fate is not a dramatic conclusion, but a gradual, almost imperceptible approach toward equilibrium with its surroundings, a quieting, not an ending. The cooling of a rogue planet is a process that plays out on timescales that dwarf the current age of the universe. A gas giant rogue planet, with its enormous mass and thermal capacity, retains its heat on timescales of tens of billions of years. The universe itself is currently about 13.8 billion years old. A large rogue planet that formed early in the galaxy's history, say, 10 billion years ago, is still carrying a significant fraction of its original heat budget today, still convecting slowly, still maintaining a meaningful temperature differential between its interior and its surface. It will continue to carry that heat for billions of years more. The warmth in its core predates the solar system. It predates the Earth. It predates every complex structure that has ever existed on any planet we know of. And it continues still, patient and enormous, moving through the interstellar dark. Smaller, rocky rogue planets cool faster because they have less thermal mass and higher surface area to volume ratios that allow heat to escape more quickly. A rocky rogue planet the size of Earth would cool to near ambient interstellar temperature over timescales of perhaps a few billion years, depending on its initial heat budget and the efficiency of its cooling mechanisms. Rocky worlds radiate their interiors away into space with a relative efficiency that gas giants cannot match. Their smaller mass means there is simply less heat stored. and their solid surfaces conduct and radiate it away over geological time. But even near ambient interstellar temperature is not absolute zero. Interstellar space is not perfectly cold. The cosmic microwave background radiation fills all of space with a temperature of about 2.7 degrees Kelvin, just above absolute zero. And a rogue planet will approach this temperature asymptotically, always slightly warmer than its surroundings, the gap narrowing towards zero but never quite reaching it on any finite timescale. Perfect thermal equilibrium is a limit, not a destination. The rogue planet approaches it forever and arrives never. The radioactive component of a rogue planet's internal heat budget follows its own separate timeline. Different radioactive isotopes decay at different rates, releasing heat as they go. Short-lived isotopes contribute strongly in the early history of the planet and are largely exhausted within the first billion years. Longer-lived isotopes, uranium-238, thorium-232, potassium-40, continue generating heat over timescales of billions to tens of billions of years. In a rocky rogue planet, the slow decay of these long-lived isotopes forms a background heat source that outlasts almost every other process in the planet's thermal history. Long after the formation heat from accretion has largely radiated away, the radioactive heaters embedded throughout the planet's rock are still working, quietly and continuously, adding their small contributions to the interior temperature. On a planet with a thick insulating atmosphere or a deep ice shell, even this modest heat can make a measurable difference to conditions in the interior. The very far future of the galaxy, the cosmological future, measured not in billions but in trillions and quadrillions of years, will be a very different environment from the one we inhabit today. Star formation is not a process that continues indefinitely. The molecular gas clouds from which stars form are being consumed, converted into stars and their remnants, and the supply is finite. The galaxy is not a closed system that recycles its gas perfectly. Some fraction is locked permanently into remnants. Some is lost to the intergalactic medium, and what remains available for new star formation diminishes over time. Over the next few trillion years, the rate of star formation will decline to essentially zero. The galaxy will gradually transition from a system of active stars to a system of stellar remnants, white dwarfs, neutron stars, black holes, and the rogue planets drifting between them. In this era, the distinction between a world with a sun and a world without one becomes almost meaningless. The white dwarfs that remain will be tiny, dim objects, cooling slowly toward the temperature of interstellar space, producing only a fraction of the light that their progenitor stars did. Any planets that survived the red giant phases of their host stars or were captured into orbit around white dwarfs later would be receiving so little energy from their dim remnant suns that their situation would differ only marginally from that of a rogue planet. The galaxy will be darker, cooler, quieter, populated by objects that persist not because they are still generating energy, but because they are simply massive enough to resist the forces that would disrupt their structure. Persistence, in this deep future, belongs not to the brilliant, but to the massive and the cold. Rogue planets, in this far future, will be among the most common intact physical structures in the universe. Their numbers will not have decreased significantly. There are no processes on these timescales that would eliminate them in large numbers. They will simply continue their galactic orbits, now perhaps more often passing the dim remnants of former stars rather than active ones, cooling toward equilibrium with an environment that has itself grown colder as the stars have dimmed. In a galaxy of stellar remnants, the rogue planets are the continuity. They were there before the last stars formed. They will be there after the last stars have cooled to darkness, and they will be there long after that, moving through a galaxy that has grown so dark and sparse that the difference between interstellar space and intergalactic space is difficult to define precisely. The galactic dynamics of this deep future are themselves worth considering. Gravitational interactions between objects in the galaxy, stars, remnants, rogue planets, continue operating over these timescales. On timescales of tens of trillions of years, gravitational encounters between objects in the galaxy will have redistributed momentum and energy throughout the system, flinging some objects out of the galaxy entirely and allowing others to slowly spiral inward. The galaxy, as a coherent structure, faces its own long dissolution, though the timescale for that dissolution is itself enormous. Individual rogue planets caught in gravitational encounters could be ejected into the true intergalactic void, the space between galaxies, which is emptier and colder and more isolated than interstellar space by a very large margin. An intergalactic rogue planet would be, by any measure, the most isolated type of world in the universe. No galaxy, no stars in any meaningful proximity, no gravitational community of any kind, moving through an expanding universe that grows emptier with every passing eon. The proton decay hypothesis, a prediction from some models of particle physics that protons themselves might be unstable on timescales of 10 to the 33 years or more, would, if correct, eventually dissolve the structure of all matter, including rogue planets. On this unimaginable timescale, the very atoms composing a rogue planet would cease to be atoms, their constituent protons quietly decaying into lighter particles and radiation. The solid body of the planet dissolving not through any external force, but through the slow betrayal of the matter it is made of. But these timescales are so enormously larger than anything else discussed here that they are effectively irrelevant to any practical discussion of rogue planet longevity. The universe at 10 to the 33 years bears no meaningful resemblance to the universe we can discuss in any other context. On any timescale that is meaningful in any human or even astronomical sense, rogue planets persist. This persistence, the quality of remaining simply because there is no process that requires an end, is in some sense the defining characteristic of rogue worlds. They are outcomes rather than processes. They formed through a process. Their interiors operate through processes. But the planet as a whole object is not consuming itself, not moving toward an inevitable conclusion driven by internal dynamics. A star's brilliance carries within it the announcement of its eventual death. A rogue planet's darkness carries no such announcement. There is no internal clock counting down, no fuel gauge approaching empty, no structural instability building toward resolution. There is only the slow leak of heat into space, the gradual quieting of the interior, the imperceptible approach toward the temperature of the universe around it. It is worth sitting with this for a moment. The rogue planet drifting through the interstellar medium right now, warming its interior with heat left over from the collapse of its formation disk, will still be drifting different only in being colder and quieter when the Sun has become a white dwarf, when the Milky Way has merged with Andromeda, when the last new stars have formed and themselves aged and dimmed and cooled to darkness. It will still be there, moving patiently through whatever the galaxy has become, intact and massive and cold, carrying the memory of its formation in its chemistry and its structure, witnessed by nothing, illuminated by nothing, persisting for no purpose other than the simple fact that nothing requires it to stop. Rogue planets are, in this sense, among the most durable objects the universe produces. They are simply, stubbornly, quietly there in the dark and the cold, for longer than most other things in the universe manage to last. Solitude, in the way we apply it to rogue planets, is not absolute. The image of a completely lone world, isolated in featureless dark with no other gravitational relationship at all, is an approximation probably accurate for the majority of rogue planets, but not the universal condition. Some rogue planets may have companions. The universe, it seems, resists perfect isolation even at its most extreme margins. Wherever mass gathers and gravity reaches, the tendency toward structure asserts itself, quietly and without exception. The most immediately plausible form of companionship is a moon. The rogue planet OTS-44, as noted in the earlier tour, appears to be surrounded by a disk of material that could produce moons through the same accretion process that forms moons around planets in stellar systems. This is not surprising. In principle, the physics of accretion around a central body depends on the mass of the central body and the availability of material, not on the presence of a star. If a rogue planet forms with enough surrounding material, or captures material during its early history, it can develop a system of moons just as the gas giants in our solar system did. The star is incidental to this process. What matters is mass and proximity, and time and rogue planets have all three in abundance. A moon orbiting a rogue planet would itself be in a very particular situation. It would be kept in orbit, not by a star, but by the planet, and it would be warmed, not by a star, but by a combination of its own residual heat, its own radioactive decay, and potentially by tidal heating generated by the gravitational interaction with the planet. Tidal heating is the process by which the gravitational pull of a larger body on a smaller one deforms the smaller body slightly as the orbital geometry changes, and this deformation generates friction and heat. It is the mechanism that keeps the interior of Jupiter's moon Io in a state of extreme volcanic activity, and it is believed to maintain liquid water beneath the ice of Europa and Enceladus. These moons of Jupiter and Saturn are among the most discussed candidates for life in the solar system, not because they have sunlight. They receive very little useful energy from the sun at those distances, but because they have heat from below, and heat from below is enough. For a moon orbiting a rogue planet, tidal heating would be available even in the complete absence of any stellar energy. If the moon's orbit is slightly elliptical, not a perfect circle, but a gentle oval, the varying gravitational pull as the moon moves closer to and farther from the planet would continuously flex the moon's interior, generating heat. This heat, combined with the moon's own internal heat sources, could maintain geological activity and, in the right circumstances, liquid water beneath an icy surface for billions of years. The process does not require a star. It does not require sunlight. It requires only gravity and an orbit that is not perfectly circular, and the slow conversion of mechanical energy into warmth. A moon of a rogue planet in this situation, warmed by tides from its parent world, insulated by a thick ice shell, perhaps harboring a liquid ocean in the dark interior, would be one of the most isolated potential environments for complex chemistry in the universe. It would have no sun, no external light, no connection to any stellar system. Its energy would come entirely from the mechanical deformation of its own structure by the gravity of its parent planet, and from the slow decay of its own radioactive inventory. And yet it would have liquid water. It would have a seafloor warmed by the heat flux from below. It would have chemistry. Whether that chemistry could ever rise to the complexity we associate with biology is a question no one can yet answer with confidence. But the physical preconditions, energy, liquid water, mineral interfaces, chemical gradients need not be absent simply because the nearest star is light years away. The darkness above the ice would be total and permanent. Below it, in the pressurized warmth of a hidden ocean, the relevant conditions might be satisfied regardless. Beyond individual moons, there is the possibility of binary rogue planet systems. Two planetary mass objects, gravitationally bound to each other, orbiting their common center of mass, drifting together through the galaxy. Binary systems are common at all mass scales in astronomy. Binary stars are extremely common. Binary asteroid systems exist in the solar system, and there is no physical reason why two planetary mass objects could not be gravitationally bound to each other. They could have formed from the same collapsing gas fragment, remaining loosely bound even as the fragment collapsed, or they could have formed separately and captured each other in a low-velocity encounter when they happened to be moving at nearly the same speed in nearly the same direction. A coincidence that is rare but possible across the separate, enormous population of rogue planets and the enormous timescales of galactic dynamics. Given that there may be hundreds of billions of rogue planets in the Milky Way alone, even low-probability encounters accumulate into a meaningful number of actual events scattered across the galaxy and across time. A binary rogue system would be a quiet, self-referential gravitational relationship, two worlds orbiting each other in the dark, each one a presence in the other's sky. The more massive of the two would be the dominant gravitational partner. The smaller would orbit around a point that lay somewhere between them, closer to the more massive one. From the surface of the smaller body, if it had a surface, the larger body would be the dominant feature of the sky. A sphere whose angular size would depend on the orbital distance, perhaps small and distant, perhaps close enough to show features if there were any features visible in the darkness. There would be no sunrise, no stellar backdrop of shifting constellations overhead. There would only be the companion, moving slowly or quickly depending on the orbital period, tracing its arc across a sky otherwise occupied by the cold, fixed light of distant stars. The orbital period, the time for one complete orbit, could range from hours to years, depending on the masses and the orbital separation. At close separations, the two worlds would sweep around each other rapidly, their mutual tidal forces strong and continuously working. At greater separations, the orbit would be stately and slow, and the tidal influence more muted. In such a system, tidal heating would operate reciprocally. Each body would be tidally deformed by the gravity of the other. The more massive body would produce a larger tidal force on the smaller one, but the smaller one would also produce a gravitational effect on the larger, deforming it slightly in turn. If the orbits are eccentric, both bodies receive a continuous heat input from these tidal forces, additional to their internal sources, potentially enough to extend the geological and thermal activity of both objects for longer than either would remain active in isolation. A world that might otherwise have cooled to geological silence within 1 billion years could be kept partially active for several billion more, its interior stirred by the rhythmic squeeze and release of its companion's gravity. The companion is, in this sense, a gift, an involuntary source of warmth delivered across empty space by the simple fact of proximity and orbital eccentricity. Whether either body in a binary rogue system could sustain conditions favorable to complex chemistry depends on the specifics: the masses, the orbital distance, the eccentricity, the internal composition, the presence or absence of volatiles. These details vary from system to system, and most configurations would likely not be hospitable to anything we would recognize as biology. But the energy source gravity, converted to heat through tidal flexing, is real, and its effects are not negligible over geological time. The binary rogue system is not merely a curiosity of celestial mechanics. It is a configuration in which two objects that would otherwise cool and darken independently instead sustain each other, however modestly, across the long dark of interstellar drift. Multi-object rogue systems, a rogue planet with multiple moons, or a binary rogue with moons of each, are almost certainly rare. The gravitational dynamics of multi-body systems tend toward instability over long timescales, especially in the absence of the stabilizing influence of a massive central star to keep subordinate bodies in order. Small perturbations accumulate. Resonances that might protect orbital configurations in a stellar system may not exist in the same form around a pair of planetary mass objects. Bodies in unstable orbits are eventually ejected or fall inward to collision. The more complex the system, generally speaking, the shorter its expected lifespan as a coherent configuration. But rare is not impossible, and over the enormous timescales and enormous population of rogue objects in the galaxy, even rare configurations exist somewhere. There are, almost certainly, multi-moon rogue planets drifting through the interstellar medium right now, small gravitational families moving together through the dark, held in temporary but real coherence by the same physics that holds solar systems together, simply at a smaller and more isolated scale. The existence of these possible relationships, planet and moon, planet and planet, central world and orbiting companions, suggests that even the extreme isolation of interstellar space does not necessarily produce objects that are entirely alone in a gravitational sense. Structure persists at many scales. The universe tends to organize gravitationally bound systems wherever there is mass and opportunity, and rogue planets, despite their separation from stellar systems, are not exempt from this tendency. They carry, or may carry, their own small gravitational families into the dark, tiny systems within the larger system of the galaxy, each one self-contained, each one moving through the interstellar medium as a unit, warmed from within, guided by its own gravity, holding together whatever companions gravity has given it. What this means, considered at the scale of the galaxy, is that the interstellar medium is not simply a void interrupted by occasional solitary worlds. It is threaded, at low density but meaningfully, with small gravitational communities, pairs of worlds, worlds with moons, perhaps the occasional more complex arrangement, each pursuing its own long trajectory through space, its internal dynamics continuing undisturbed by the stellar environment it long ago left behind or never belonged to. These communities are dark. They are cold at their surfaces. They are, from any practical human perspective, unreachable with current technology and almost certainly undetectable in detail with current instruments. But they are there, moving through the galaxy with the patient indifference of all large gravitational systems, carrying their internal heat, their orbital mechanics, their chemical inventories, and perhaps, in some cases, in some hidden ocean under some unnamed ice, the slow, ancient patience of chemistry working toward complexity in the dark. Solitude for a rogue planet is not guaranteed. The galaxy is vast and gravity is persistent, and wherever mass exists in sufficient proximity, structure follows. Even at the farthest remove from any star, the tendency toward organization reasserts itself at whatever scale is available. A planet and its moon. Two planets bound. The universe does not easily permit perfect isolation. It tends always and at every scale toward the companionship of gravity. And so we come, gently, to the place where all the threads of this long night can be gathered back together, not tied tightly, not resolved into a conclusion that announces itself, but gathered softly, the way a story gathers as a listener approaches sleep, its edges softening, its central quality becoming clear. The central quality of rogue planets is this: they are complete. Not complete in the sense of finished, not complete in the sense of perfect or sufficient or satisfied, but complete in the structural sense, the physical sense. a rogue planet carries within it everything it needs to continue being what it is. Its gravity shapes it. Its interior warms it. Its atmosphere, if it has one, insulates it. Its rotation gives it time. Its mass gives it persistence. None of these things require a star. None of them are borrowed from the outside. They are intrinsic, original, entirely the planet's own. This is worth sitting with for a moment, here at the end of the night, when the ideas have had time to settle and the images have had time to become familiar. A world that is complete in itself. A world that does not reach outward for warmth, or light, or organizing structure, because all of those things, or the version of them that matters, already exist within it. The gravity that holds its atmosphere close is the gravity of its own mass. The warmth that keeps its interior from solidifying entirely is the warmth of its own formation and its own atoms slowly releasing energy in the dark. The rotation that gives it something like a day is the spin it inherited at birth, conserved across billions of years, because there is nothing out here in the interstellar medium substantial enough to slow it down. The question posed at the beginning of this journey, if there is no star, what allows a world to remain warm at all, has its answer now, and the answer is quieter and more fundamental than any special mechanism, any exotic process, any dramatic exception to the rules. The answer is simply the planet itself. The formation heat still bleeding outward from an interior that has been cooling for millions or billions of years, the patient radioactive decay turning atomic mass into warmth at a rate determined entirely by the physics of the nucleus. The atmospheric blanket holding that warmth close rather than letting it escape entirely into the cold of space. These are the sources. These are, in the most literal sense, internal belonging to the planet, arising from the planet, sustaining the planet in its long journey through the dark. There is something quietly reassuring in this, if you allow yourself to receive it. The idea that warmth does not have to come from outside, that a world can carry its own supply of it, impermanent and gradually diminishing, but real and present and sufficient for geological spans of time. That the absence of a star does not mean the absence of warmth, not immediately, not for billions of years. These worlds are not cold and dead from the moment of their ejection. They are warm, some of them, and they remain warm for very long stretches of time, long enough for processes to operate, long enough for oceans to exist beneath ice, long enough for weather to circulate in the deep layers of a gas giant atmosphere, long enough for a magnetic field to pulse quietly outward into the surrounding space, long enough for something that could, in another context, be called a world in full operation. It is worth returning, one final time, to the warmth beneath the ice. Among all the images that rogue planets offer, this one has a particular quality of stillness and persistence that seems right for the end of a long night. Somewhere in the galaxy, on a rogue planet whose surface is locked in ice cold, featureless, receiving no starlight, producing no reflected glow, there may be water in its liquid form. Not at the surface, not visible, not accessible to any instrument we currently have, but present in the deep interior, pressed between the descending weight of the ice above and the rising warmth of the geothermal heat below. An ocean in the dark, maintained by nothing more exotic than the slow bleeding of formation heat and the patient work of radioactive decay, insulated from the cold of space by the ice that caps it. That ocean, if it exists, has perhaps been liquid for longer than the Earth has had oceans of its own. It formed in the dark, it has remained in the dark, and it will remain there long after the ice above it has been undisturbed for 1 billion more years. There is no light in that ocean. There is no tide from a moon, no wind from a storm, no surface to break against. There is only the slow, dark circulation of water responding to the temperature differences between the warm floor and the cool ceiling of ice, the convective turning of a body of liquid that has nowhere to go and no reason to hurry. If there is chemistry happening there, if the warmth of the seafloor is producing anything complex from the minerals and gases dissolved in that water, it is chemistry that has been running, unobserved, in complete isolation, for an enormously long time. The galaxy holds them, these rogue worlds, in the only way it holds anything, by the slow arithmetic of gravity, the accumulation of mass acting on mass across the distances that separate every object from every other one. They do not fall. They orbit. They take their place in the same broad galactic structure as the stars, following the same large-scale trajectories, participating in the same slow rotation of the Milky Way around its center. From far enough away, from a vantage point so distant that individual stars are invisible and only the broad galactic structure is visible, rogue planets are simply part of the mass of the galaxy, contributing their small but real gravitational presence to the whole, indistinguishable in their contribution from any other planetary body. And the Milky Way, for its part, does not distinguish between them and the stars. The galaxy's gravitational potential is shaped by all of its mass, together the stars, the gas clouds, the dust, the dark matter that threads through the whole structure, and rogue planets are part of that mass, each one small but real, each one bending space very slightly with its presence, each one pulling very faintly on everything around it. They are structural participants in the galaxy, not passengers. They belong to it as fully as the stars do, as fully as the nebulae and the open clusters and the ancient globular clusters that orbit in the halo. They are the Milky Way, in the same quiet way that every component of a large and complex thing is that thing. There are many billions of them. They are distributed throughout the disk of the Milky Way, moving quietly through the space between the stars, each one a world in the fullest sense of the word, each one carrying its own warmth and its own structural integrity, each one drifting on a trajectory that will continue, largely unchanged, for longer than most stars will exist. They are, in a sense, patient, in a way that stars cannot be. Stars are burning, consuming, transforming toward their inevitable ends, while rogue planets simply continue, not burning, not consuming, just carrying forward the mass and warmth and structure they were given at formation. A star, however brilliant, is always spending itself. The light it produces is paid for with hydrogen, and the hydrogen is finite, and the day will come in millions or billions of years, depending on the star's mass, when the account runs low, and the star must change what it is in order to continue. It will expand, or collapse, or shed its outer layers, or end in an event so large that the word ending seems inadequate. It will transform. And in transforming, it will cease to be what it was. A rogue planet does not spend itself in this way. It has no fuel to burn. Its changes are all in the direction of slower, quieter, cooler, to a gradual approach to the temperature of the space around it, but an approach that is measured in timescales so long they have no meaningful name at human scale. It does not end. It persists. And in persisting, it outlasts the very stars that once illuminated worlds like it, in systems long since transformed or gone. The sky above a rogue planet, the permanent star field, the Milky Way that never disappears behind a rising sun, the sky that is always the sky of interstellar space, is also the sky of extraordinary patience. The stars in it do not move on any human timescale. The Milky Way does not shift position in any year or century or millennium that matters to a human observer. The sky is stable, continuous, unchanging in any way that an observer standing on the surface could detect in a lifetime or in many lifetimes. It is the sky of deep time, the sky that a body sees when it is old enough and slow enough to be indifferent to the short rhythms of stellar systems. And there is a certain kind of rest available in that image, if you allow it. The sky that does not require anything of you. The stars that do not rise or set on any schedule you are expected to keep. The slow, continuous turning of the planet itself, measuring time in a way that has nothing to do with appointments or seasons or the particular demands of any given day. Just the turning and the stars, and the long quiet of interstellar space extending outward in every direction without a visible boundary. Perhaps this is what rogue planets, considered as a whole class of objects, most gently suggest to anyone thinking about them at the end of a quiet night. That existence does not require adjacency to a source of light. That warmth can be internal, sufficient, and slow. That the darkness between the stars is not an obstacle or a threat, but simply the environment, the continuous medium through which worlds travel on their long, patient arcs. That a planet can be fully itself, fully structured, fully warm enough, without a sun to illuminate it, or define its seasons, or count its years. Each rogue planet encountered tonight had its own particular character. PSOJ 318.5-22, young and warm, trailing iron clouds through a high atmosphere, still glowing with the heat of recent formation. WISE 085 5-0714, one of the closest known free-floating worlds to our own solar system, so cold that water ice may form in its outermost atmospheric layers, almost invisible even in infrared, quietly drifting through a corner of the galaxy that it shares with us in the most distant and unannounced way. SIMP J013656663 plus 09333473, with its strong magnetic field and its quiet auroral emissions crackling in radio frequencies that no ear is present to hear, a persistent electromagnetic presence in the interstellar medium. OTS 44, surrounded by its disk of material, building its own small architecture in the dark, a planet at the center of something that might one day become a system, however modest. Each of these is a real place. Each of them exists, tonight, in the same universe that contains this room, this quiet, this moment at the end of the day. The distance between here and there is enormous, measured in light years, in the time it takes light itself to travel across the intervening space, but the fact of their existence is not distant. They are real, their processes are real, their warmth and their cold and their slow rotation are all real, happening continuously, without pause, without any awareness of being observed or thought about. Somewhere in the galaxy tonight, a rogue planet is continuing exactly this, moving slowly through the interstellar medium, carrying its own warmth through the quiet dark. Its atmosphere, perhaps circulating in slow weather patterns, driven by geothermal heat from below. Its magnetic field extending outward into the sparse interstellar plasma. Its surface or deep cloud layers as cold as the space above them, but its deep interior still carrying the warmth of formation, the warmth of radioactive decay, the warmth that is entirely its own, that belongs to no star and needs none. It has been doing this for longer than the Earth has existed. It will continue doing it for longer than the sun will exist. It asks nothing of the stars around it. It gives nothing in return. It simply moves through the long quiet, turning slowly on its own axis, measuring its own time by its own rotation, unhurried, unannounced, complete. The galaxy turns around it, slowly. The stars it passes are irrelevant to its internal processes, noticed by no mind on its surface, affecting it only by the faintest gravitational whisper. It moves through regions of denser gas and sparser gas, through the broad influence of spiral density waves passing through the galactic disk, through the slow drift of time at the largest scale. Other rogue planets pass at distances so enormous that their gravitational effect on each other is negligible, each one pursuing its own independent arc, each one alone but part of the same vast, quiet population. And through all of it, the rogue planet remains. Not unchanged, it is slowly cooling, slowly settling toward the temperature of its environment, slowly losing the last traces of the geological dynamism of its youth, but present and intact and continuing. This is the long, quiet companion. This is the planet that travels without a sun, sustained by its own warmth, participating in the galaxy without belonging to any of its stars, persistent beyond the careers of the brightest and most visible objects in the sky. This is the rogue world, in the dark, carrying itself forward. There is a word for this quality in certain traditions, the quality of persisting without requiring external validation, of being fully what one is without needing a source of light from outside to confirm it. It is a quality that the universe seems to produce, almost incidentally, in the process of making worlds. Some worlds find stars and orbit them, and are illuminated and warmed and structured by them for as long as the star lasts. And some worlds do not find stars, or lose them, or never had them, and those worlds discover in the most purely physical, non-metaphorical sense that they were already complete, that the warmth they needed was already inside them, that the time they needed was already ticking in their rotation, that the structure they needed was already held together by their own gravity. And as you drift, here at the end of this night, toward the kind of sleep that comes after a long, slow journey through large ideas, as the specific details grow softer and the overall quality of what was described becomes more ambient than precise, as the names of specific objects blur into the general image of dark worlds moving through dark space, perhaps you carry something of this quality with you into rest. The warmth that does not depend on an outside source. The patience of things that simply continue. The sky of deep time, full of cold stars, never requiring a sunrise to make itself real. The rogue planets will be there tomorrow. They will be there the night after that, and all the nights after that, for a duration of time that the word long does not adequately describe. They will continue their slow, quiet work of being worlds, in the dark, warming themselves from within, turning on their axes, following their galactic arcs, asking nothing of anyone, needing nothing from outside that they do not already carry. And you can rest now, in the knowledge that the universe is very large and very old, and very full of things that continue quietly in the dark worlds and warmth and the slow turning of the galaxy, and that none of it requires your attention tonight. Sleep well and good night.